This is Kung Fu Review video number 3. This is on bonding. So what I'm going to do is I'm going to go over the key things you need to know for bonding. So first and foremost, when we're talking about bonds, what we talk about is like bond designation. Basically, a sigma bond is the first bond that forms between a molecule. So for example, let's take our friendly water molecule here. If you draw the Lewis structure of the water molecule here, there's a couple things I want you to be aware of. Is that represents a sigma bond and that represents a sigma bond. So when we talk about a sigma bond, is a single bond. In a double bond, you have one sigma and one pi bond. So for example, if I draw carbon dioxide, if you look at there's a molecule of carbon dioxide right there. It has one of the bonds is a sigma, so I'll make that purple. The other bond in there is going to be a pi, and then finally in a triple bond you have one sigma and two pi bonds. So when we talk about designating a bond and what it is in a single bond, double bond, triple bond, you need to know the sigma pi. Bond order. Bond order is basically when you take the number of bonds divided by however many clouds you have. So I have two bonds here and they're in two clouds, so the bond order overall. In a single bond is always 1, in a double bond's 2, and a triple bond's 3. It's whether or not you have a resonance structure. When you have a resonance structure, you kind of use the bond order to decide the difference between lengths and energy in two molecules, in bond lengths anyway. Longest bond is always going to be a single bond. The intermediate is a double, and as you increase the number of bonds, the bonds get shorter. So a triple bond is the shortest. Finally, bond energy. Single bond has the least amount of energy, increases with a double bond, and a triple bond has the greatest amount of energy. So those are basically the key things you need to know about bonds. Now, polarity of a molecule, we've talked about this. When we talk about polarity, we're talking means that basically a molecule has a dipole, right? So a dipole means you have one side of it that is going to be more negative and one side that's going to be more positive, commonly shown with a symbol that looks like this. 3 things determine whether or not a molecule is polar. If it's diatomic molecule and there's a difference in electronegativity, it's automatically polar. That's where you can use the focal and brick ship, meaning if it's 2 different elements on this list, like for example, if you just had a molecule with nitrogen and oxygen bonded together, obviously it would be a dipole. Oxygen is stronger because this is the most electronegative element is fluorine, and then as you go down the list it gets lower. But if you're comparing, like we did the other day, HCl and NO bonded molecules, if you're comparing the 2 of these, there's a greater distance between H and Cl using focal and brick ship than N and O. So that's an easy way to kind of look at it. Now, if a molecule has different terminal atoms, it's polar, because basically it means the molecule is not symmetrical. So even if you had a molecule that has polar bonds, if it's a symmetrical molecule, those bonds will cancel each other out, leaving it not as a dipole, but as a nonpolar molecule. So I'll show you that in the next page. If there's a lone pair of electrons on the central atom, automatically it's going to make it polar. You will see this term a lot on the AP exam. They will talk about a nonpolar molecule that contains polar bonds. What are they talking about? Well, they're talking about this. If you look at a molecule like this, carbon tetrachloride. Carbon has a electronegativity value of 2.5, chlorine is 3.5. So overall, that bond is polar, that bond is polar, that bond is polar, that bond is polar. So this molecule contains polar bonds. So it has 4 polar bonds in it, but because it's symmetrical or has the same type of terminal atoms, it's nonpolar. Just like BF3 is an example, it's nonpolar as well because the bond itself between the 2 atoms is polar, forms a dipole, but the dipoles cancel because the molecule is symmetrical. Whereas this one, we talked about this, is only being made of 2 atoms is polar. This one with a lone pair of electrons would make it polar, and then this reason this molecule is polar, again, the dipoles don't cancel. So that's when we talk about a molecule that is nonpolar overall, that contains polar bonds, really referring to a symmetrical molecule. That's what you would look for. Resonance. What is resonance? It means it has a double bond that can be in multiple places. Here's a common example of a resonance. If you had to draw SO2, SO2 looks like this. This is an example of a resonance structure, so it can be drawn 2 different ways. So on the AP exam, you would do double arrows, and I could draw it like this. Now, if you're comparing something that has a resonance structure versus something that doesn't have a resonance structure, it's hard to figure out strengths or bond lengths. The easiest thing to do is use bond order. For example, the bond order of this, there's a total of 1, 2, 3 bonds in 2 clouds. So then basically overall, the bond order of this is going to be basically 1.5. So your bond order in this case is 1.5. So it's in between a single bond, which has a bond order of 1, versus a molecule that has a bond order of 2. So it's in between. Because they'll ask you a lot of times on the AP exam, like to compare carbon dioxide. Here you have carbon dioxide here. The bond order of carbon dioxide is 2. Because it's 4 total bonds, 2 clouds, so it's going to be 2. If you compare that to a carbonate ion, go to draw a carbonate ion right here. Carbonate ion has a resonance structure to it. So when you draw a carbonate ion, it's got a resonance structure. So basically what you have to do with this one is you take the total number of bonds 4 divided by the number of clouds 3, and then basically you end up with a 1.33 value. So it's basically 1.33, which basically means the bonds are shorter than a single bond but longer than a double bond. They contain less energy than a double bond. You can use the bond order to kind of rank them going back here. It goes back to the idea we used in this chart here. You know, this is bond order of 1, bond order of 2, bond order of 3. Allows you to compare these properties of the bonds. So keep that in mind. It's another point. Incomplete octets. There are some atoms that are stable with less than 8. Examples, hydrogen is always an end cap when we draw Lewis structures. The most common example used on the AP exam is boron. Boron only bonds on 3 sides. Helium is another one that basically is happy with only 2 electrons, or stable with only 2 electrons. The one that's used the most often on the AP exam, whenever you see boron with, for example, boron trifluoride in this case, you know the molecule is nonpolar because boron's only going to form bonds on 3 sides. So that it helps to basically have that memorized. All right, next thing, expanded octet. Basically, you have to have a D subshell available so the central atom can have more than 8, but never more than 12. Because remember, the reality is the most you can have is 6 clouds. The 2 elements that do this the most often are phosphorus and sulfur, so they can have up to 5 here. You could have a total of 6 bonding sites, or basically 12 valence electrons in the bonds around sulfur or phosphorus. Those are the common ones. So on the exam, on the AP exam, you will see a lot of like PCl5. You could see SF6. Those are molecules you will typically see. Since those are expanded, you always want to draw them to make sure, but they're definitely expanded octets because of those 2. VSEPR. VSEPR theory is based on the idea that valence shell electrons repel each other. We know that the idea of repulsion, when we talk about Coulombic interactions again, remember like charges repel. So if you have a negative and a negative, they repel. Well, electrons repel each other. So the idea is the VSEPR geometry comes from the idea that they're always going to be as far apart as possible to minimize repulsion. So lone pairs, the other key part is lone pairs are more repulsive, so they alter the shape more than electrons locked in bonds. The idea is kind of like I was telling you in class the other day. If you take a molecule that, for example, is a tetrahedron, I'll try and draw it as this is a tetrahedron. If you bond on all 4 sides and there's atoms there, the bond angle is 109.5. If you take that same situation, a great example is NH3. You bond atoms on 3 sides and you put a lone pair of electrons there. Lone pairs of electrons, and that's what the VSEPR theory is all about. Lone pairs of electrons. As you add more lone pairs to a central atom, it causes the bond angle to crunch down. So the bond angle no longer is 109.5. It's closer to basically 107. 107 because the lone pairs of electrons are more repulsive. So the bonds you see here will basically be pushed down more. And that's the whole idea behind the VSEPR theory and shape. So when we talk about geometry and the geometric shapes, and you're looking at the different geometric shapes, you know, we can start, if we start with 3 atoms here, you have 180, this is 180, and then as you add another one, it becomes 120, and then the key thing to remember is a lot of the bond angles come off the idea of a tetrahedron being 109.5. As you add lone pairs of electrons, you cause the other bonds to basically crunch down. That's the key thing. So that's basically everything you need to know about bonding. The one other thing that you kind of need to know about bonding that I didn't really think to put a slide on, but I'll do this really quick, is what's called formal charge. When you draw a Lewis structure, one of the things you can do is you can just assign formal charge. Formal charge is easy. You take the valence electrons that an element normally has, like oxygen normally has 6 valence electrons, carbon and oxygen, like in this molecule. Carbon has 4 valence electrons, oxygen has 6. And what you do is you subtract the valence electrons, so the valence electrons minus what we call assigned electrons. Assigned electrons are the number of electrons that you see in the molecule when it's drawn. The way it works is dots count as 1, 1, 2, 3, 4. Lines count as only 1 assigned electron as well. Normally lines count as 2, but in this case oxygen has 6 assigned electrons, so 6 minus 6. We would say the formal charge of that oxygen is 0. Carbon here, carbon has normally 4 valence electrons. You have 1, 2, 3, 4 dots there. 4 minus 4, the formal charge of that's going to be 0. Finally, if you do the same thing for oxygen, 0. The ideal Lewis structure is you want all the elements in a Lewis structure to have a formal charge of 0. It doesn't always work that way, but the best Lewis structures are the ones that have the most formal charges of the elements in the structure, 0. Okay? Last thing is if you have to do a hybridization of a molecule. Let's say they give you a molecule that looks like this. CH3, CH2, CH3. When you have a chain, remember the first thing you want to do is you want to connect the chain of carbons together. So I connect the chain of carbons. The number of H's listed after is the number of H's that are directly connected to the molecule. So in this case I have C with 3 H's, so I basically put an H here, H here, H here. This has 2 H's, and this has 3 H's. That is called a structural formula. So it basically lists how you need to write the Lewis structure, and then when you go to do hybridization, all you're doing, remember, is you're counting clouds. So I basically look at the clouds here. 1, 2, 3, 4. We would say that would be sp3. 1, 2, 3, 4. 1, 2, 3, 4. So you go through and you do the hybridization of each central atom one at a time when you try and find the hybridized clouds. All right? If you have any other questions or anything else I can help you with, I'll be to school in the morning, but otherwise you need to definitely prepare. Your review quiz is tomorrow, and make sure you bring all your super notes to class because I'm going to check your entire notes package to make sure it's updated. Have a nice evening.